Okay, we're going to take a look at a couple of existence theorems. So these are picture theorems. These are just things, when we say existence theorem, they don't really do much. They leave all the work for you, but they just tell you that if you meet the criteria of the theorem, then it guarantees the existence of something that you can go find. So this is called Raleigh's theorem, and does this make sense? Let's just think about this in terms of a picture. So let f be continuous on this closed interval, from a to b inclusive, and differentiable on the open interval, right? So think what that means then. What does that mean in terms of the shape of a graph if a function is continuous on the closed interval? What's that tell you about graphing the function? No breaks in the function? That's true, but there has to be a max and a min from the extreme value theorem yesterday. In terms of my graphing it though, in terms of my pen and the board, it means if I put my pen on the board, it never leaves it. Good. So if I'm going to go from, let's say this is A and that's B. If I put my pen down somewhere at an X value of A, I'm going to graph something without picking my pen off the board until I get to B. Okay? So that's what continuous means. Good. So that's one thing we have to consider. Now, what about differentiable? What's that mean, by the way? What's the definition of the word differentiable? Okay, it has a derivative, right? The derivative exists. Take the derivative of it. So if it's differentiable on the open interval, then what does that tell you about the nature of the curve?
If there's at least one
Well, what does it tell you? Now think about if it has a defined derivative every place between A and B.
It's not a defined view, it's not a flat line.
Say it again.
It's not a flat line.
Well, it could be. Then it would just be 0. That's defined. But think about the things it couldn't be.
It couldn't go straight up.
Okay, it couldn't have a vertical tangent line. There's one thing. What else?
No valid.
Okay, of what kind?
Sharp.
Sharp. Because we can't, right? Because we can't have sharp corners. Right? Derivatives don't exist at sharp corners, right? Okay, yeah, but now we're critical numbers. Let's remember the definition of a critical number. Critical numbers are just the values of x where we might have peaks or valleys, right? Peaks and valleys could be sharp corners though, right? There's two places where we look for critical number. Critical numbers exist at two places, where the derivative has a 0 value or where it's undefined, right? But if it's going to be differentiable, we know that if we think back to when we first started talking about derivatives, we said that derivatives can exist where there's a break in the function, where there's a vertical tangent line, right? Or where we get a sharp corner, right? So that tells you that I can't have, it's got to be, and there's the math word we use to combine these two things. Pick a better color. So that plus that means it is smooth on the closed interval between A and B. That's the word we use. A smooth function is one that's continuous and differentiable because I can't pick my pen up and I can't have any sharp corners, right? So it means that this function has to do something. We don't know exactly what it is, but it can't do that, right? Can't do that, and it can't do that kind of a thing, right? So it's got to do something like that, right? Between that point and that point. Okay. Well, if that's true, then let's just say if f of A equals f of B. So I don't know if I drew it that way. Maybe I didn't, but pretend I did. So there's the point B, f of B, and here's the point A, f of A, right? If those are equal, then does it make sense that there has to be at least one number in number C between A and B such that this is true, that the derivative equals 0? Right? How could I not have that happen? If this line right here has a slope of 0, and I'm going to draw a smooth function right? It can't have any sharp corners. There's no way that I can avoid having at least one place where I'm gonna have a horizontal tangent line. Everybody see that? In order to do that, I would have to violate one of those two criteria. Right? I could do it now, if I wanted to cheat, I could do it this way. If I had a function that went like that, then I can do it without ever having a horizontal tangent line, but that's not allowed, that's not smooth. Right? It's going to be smooth. If there's a positive slope here, it's going to have a negative slope somewhere else to get back down, isn't it? And what's got to be in between positive and negative, it's got to be a zero slope, right? Everybody buy that? I'm not going to prove that one to you today, but does that make sense conceptually? Okay? Say it again. So,
The blue line, where did you get that?
okay,
That
because
was
we know that because of this. Because the y values at A and B are the same, right? And so whatever y value, think about this in terms of an ant walking in the mountain. If this is the altitude of the ant right here, and he's going to get back to that same altitude at the end, and there's no sharp peaks in this mountain range, then he's got to walk over a peak or a valley or through a valley at least once, where it's going to be, he's going to have a horizontal tangent, right? Okay. Yes.
So f of a equals f of b means in every case a is equal to b.
No, A is not equal to B. A is different than B, but f of A, so the y value here and the y value
Oh, yeah,
here
never mind.
would be the same.
Yeah.
Okay. Now that's kind of a cool result. I mean, we can see that that works, but it's a little bit limited because how often are f of A and f of B necessarily equal to each other? Wouldn't it be better if we said something maybe like we're just going to tilt this thing, right? It'd be more generally useful. What if we said f of A doesn't have to equal f of B? We could instead make a slightly different graph, maybe something like this. Something like that. So here's the point A f of A, and here's the point B, oops, f of b. Okay, this time they're not equal, right? But if this function, if we maintain, if we preserve the criteria of that Raleigh's theorem, so the yellow graph has to be smooth, continuous and differentiable, right? Then what do you think we could say about this function? If we take that to be the secant line connecting A f of A and B f of B, there's still something important to mix. So what do we what do you think we could say? There's still something that has to happen at least once. What do you think that is?
The line has to.
You still gotta go over.
Still has to go through.
The secant line goes through the.
It doesn't ever have to have a zero slope this time, does it? Right? I mean, it looks like maybe it might there, but it doesn't have to, right? It never has to have a horizontal tangent, but something has to happen equivalent to what happened for Raleigh's theorem.
It has to go over here.
Line parallel to the secant.
Okay, there has to be at least one place where the slope of the function equals the slope of the secant line connecting the endpoints, right? And we can see where then it looks like there's two places here, doesn't it? Looks like there's one place right there, right? And maybe one place right there where we can just call these, let's call them C1 and C2. There has to be at least one place where the slope of where the value of the derivative equals the average rate of change of the function on that interval. So slope of the secant line equals the slope of the tangent line, right? Make sense? Okay, and we really just accomplished that, you see, by just tilting Raleigh's theorem. It's really all we did, right? Only this time, instead of the slope of the secant line being 0, we're saying, well, it can be something different, right? But it still holds. So this is a more useful theorem. It's kind of a generalized Raleigh's theorem. We call it the mean value theorem. So that's the one we're going to we're gonna hang on to, because that one includes Raleigh's theorem. If f of a equals f of b, I just get 0, right? For my derivative, okay? Okay,
Slow
so,
down.
so,
Let me catch up.
sure. So let's, once you guys, and I'll publish this today, so this will be on, the PDF will be up today. So those can be your notes if you want. So let's make sure, let's dissect this and make sure all this makes sense. So if f is continuous on the closed interval and differentiable on the open interval, that just means it's smooth on the interval, right? It's an easier way to say it. So that part tells us smoothness. And then what about this other part then? There exists a number c, at least one, maybe multiple, between a and b where this is true. Well, what does this mean? What's f prime of c? Okay, good. That's the
The slope.
the derivative at c, so that's the slope of a tangent line at c, right? So we're saying here, slope of the tangent line at x equals c equals, what about over here? What's this saying?
Isn't that just the slope of the secant line?
Secant line, yeah, right? That's just rise over run between a and b, isn't it? Right? So this is slope of the secant line from a to b, right? So the slope of the tangent equals the slope of the secant. So let's try this. What kinds of questions do you do when you're asked about using the mean value theorem? How would we apply this? Okay, so let's try a couple problems. Go back, sure, I'll go back. There we go. All right, so let's pick a couple problems here. How about, we good?
No, sorry.
Okay, fine. Okay. Uh-huh. Okay, so let's try this one. So we want to we're going to apply the mean value theorem if it applies. If the mean value theorem applies, then we're going to find C. And if it doesn't apply, why? Tell us why. Which criterion does it fail for smoothness? Okay, so how about, let's try this guy. So what if we have f of x equals x times the quantity x squared minus x minus 2 on the closed interval from -1 to 1.
What's the 28, 30, 34?
Oh, that's for me. Those are just the problems I'm going to use in the book that I liked. You don't have to write that down. Okay, what are we going to do? It's hard.
No, that's
Okay. So up here doing stuff, so I get kind of warm. All right, so what are we going to do here? Differentiate, sure. Okay, now let's talk about the derivative, right? So how are we going to do this derivative? Product rule? You mean, what do you, by factor out, are you sure you mean factor out? Or do you mean,
Expanded.
we could factor that, sure. But what do we, if we want to take a derivative,
You could just,
it'd be easier to just expand that out, right, to distribute the x, right? Because we don't want to have to deal with the product rule, and especially if we factored that, then we'd have a product rule involving 3 factors, right? So let's distribute the x. That makes things a lot easier. So we'll rewrite this as x cubed minus x squared minus 2x. So then, what is f prime?
3x squared minus 2x minus 2.
Good. Okay, so there's our derivative. So there's part of it. Now, in order to apply the mean value theorem, we want to know where the derivative does what. Well, first of all, does the derivative exist on this interval?
Yeah.
Sure, right? The derivative is a polynomial. Polynomials are well behaved. They exist, they're everywhere, right? They're continuous on the entire real line. This is also a polynomial, isn't it? Right? If I distribute the x, we can see that this is a polynomial also. So we know that both the function and the derivative are defined everywhere. So it's smooth. We meet the criteria, right?
Would we only worry about it if it was like a fraction or something?
Yeah, if it was a fraction or if it was a trig function or something where you could end up with some place where it's or a piecewise function where you'd have a sharp corner or something like that, absolute value function maybe, okay? So now what? We've got our derivative. We need to know the slope of the secant line, right? And then we'll just ask, where does the derivative have that value? So the slope of the secant line. What is f of b? So what's a and what's b? Negative 1 and 1. Good. So here's our a and b just define the end values of the interval, right? So what is f of b? If I evaluate my function at 1, what do I get? Negative, here's my function. Negative
Negative 2.
2, is that right, negative 2?
Yeah.
So we get negative 2 minus, what's f of negative 1? So that's going to give me negative 1 minus 1 plus 2, right? So that's going to be 0, isn't it? Do you agree? Okay. Over b minus a, over 1 minus negative 1. So we end up getting negative 2 over 2, which is what? Negative 1. Okay, so that's the slope of the secant line. And so then what we're going to do is we're going to take the yellow and the blue and make them green. See, that's the kind of thing you learn in teacher school. You just can't go through years of training for that kind of sophistication. So we'll just set the derivative equal to negative 1 and solve, right? Because we want to know, where is the derivative equal to the slope of the secant line? And by solving that, the math gods are going to tell us the x values where it happens. So what do we do to solve that? Okay, add 1 to both sides. So I get 3x squared minus 2x minus 1 equals 0. So, okay, so now we're going to go bottoms up. Is that what you're thinking? Okay, sure. We can see if this factors. Now, I would say you can certainly do bottoms up, and that's quick, and it's a great way to do it. I would say there's a couple things you always want to maybe do first when you're doing solving quadratic equations. Let's always just check the value of the discriminant first to see if we're going to get real solutions. So what's the discriminant?
2.
Remember that? Algebra 2 stuff.
Is it something about the exponent?
No. The discriminant is just, if you think about the quadratic formula, what is the quadratic formula? X equals,
Negative b plus minus square root.
okay, square root.
B
Or
squared
c.
minus 4ac over 2a.
Okay, so this is the discriminant. Because it discriminates between, that's the number that discriminates between complex solutions with imaginary parts and just pure real answers, right? How come? Well, because that's the square root. If the value of b squared minus 4ac is negative, what do you get for sure? Yeah, you get two complex conjugate solutions with imaginary parts, so they're right non-real. What if the discriminant is equal to 0? Then you get negative b plus or minus 0. Wasn't that just one answer, right? So you get one solution if the discriminant is 0. And if the discriminant is positive, well, we're going to get two different real solutions, one for the plus sign and one for the minus sign, right? So it's always a good idea when you're solving a quadratic equation, just really quickly just say, okay, is that, I don't even know the value, just a sign, positive or negative. Well, we can see right away that b squared minus 4ac has to be positive, right? Because b squared is positive, and negative 4 times 3 times negative 1, I'm multiplying an even number of negatives. So that term's positive and that term's positive, right? We can just do that in our head. We can just see, okay, well, we know we're going to get solutions, so now we can go find them. But there's no sense wasting time if the discriminant's negative and you're looking for real solutions, right? Okay, so then we could use, the quadratic formula. We could complete the squares. There's a ton of stuff we could do. I would say, here's how I approach this. And I'm not saying this is the best way to do it. This is the way I would do this one. I would say 3 is not a high, it doesn't have a high level of, well, I want to say this. It doesn't have very many factors. It's only 1 and 3, convenient factors, right? Integer factors. Negative 1 only has, 1 grouping. So it's easier to me to just trial and error this and just say, well, what's going to happen here? Either we're going to have, if this thing factors, we know that we have to have, conveniently, we're going to have a 3x and an x, because there's no other convenient way to build a 3x squared from the first terms. And what are my choices for the second terms of my factors? They have to multiply to negative 1. So either I've got a plus 1 and a minus 1, or I've got a minus 1 and a plus 1. Just check them and see if any of those work, right? So if we take the top ones, does that work? I'm going to get 3x squared minus 3x, right, plus x. That works, minus 1, doesn't it? Bottom one doesn't work. I'd get positive 3x minus x, so those fail, but those work. You see what I'm saying as a strategy? Now, I wouldn't do that. If this were like a 12 and this were a 8 or something, that's not worth doing. There's too many possibilities. You could waste a lot of time. But if it's just like 1 there and 1 there, why not do it that way, right? So then we end up with 3x plus 1 times x minus 1 equals 0. So what are our solutions? Negative 1/3 or 1. Now, if we look at the directions on a problem like this, so I guess you don't see the directions. I'll read them to you. It says, find all values of C in the interval A to B guaranteed by, or all values of C guaranteed by the intermediate value theorem. That's the way I'll probably say it on a test. So what are the values guaranteed? Those are only the values between A and B, right? So our interval goes from negative 1 to 1. So which of any of these are between our endpoints? The negative 1/3 only, right? This is on an endpoint, so it's not, this has nothing to do with the mean value theorem. Does that make sense? So this one we can get rid of. It's not in A to B, which is negative 1 to 1. This is a good one right here, though. That one is. Okay? Make sense? Okay, let's try one more. Let's try, oops. You remember the next one was, oh, it's 30, wasn't it? Yeah, 30. Oh, okay, let me go back. So what we found is, this is our answer. We found there's only one place between negative 1 and 1 where the slope of the function equals the slope of the secant line. Let me throw it on Desmos and you can just see it.
Wait, so
It is, yeah. So at x equals -3, that's where the function has a slope of -1. You can see it graphically on Desmos. This will be good. Desmos is so helpful. Do you guys remember, you have it written in your notes, what was our original function?
X.
X.
Wait,
You-
like the
Doesn't matter.
problem that.
Yeah, so it was f of x
X times
equals,
x times 1 is d of x squared minus x minus 2.
okay, so there it is. And we went between the points,
-1, 1.
yeah, how do I do this? Let me say, like, I can't remember how to do this. Oh, anyway. Okay, so we get the point -1 f of -1 and the point 1 f of 1, right? Okay, and so if we create a line through those points, I can't remember totally how to do that. But what we can see what that line's going to be. I'll just graph the line. Whoops.
This mean negative x minus 1.
There we go, and I'll just make it blue. So, everybody agree that's our secant line? Okay, so we want to know, where does the function have a tangent line that's perpendicular to that? Yeah, and you can see where it's going to be. It's going to be right there, isn't it? Right? It's going to be that line that goes through at 1/3. Like if we do the derivative, I think I can actually do this. This is pretty cool. So let's do g of x equals f prime of x. There's our derivative. And so we can turn that one off, but then I can do g of 1/3. Why did I get that? Oh, -1/3. There we go. Thank you. There we go. -1. Okay. And so if we do, I don't know how to, I'm not sure how to do a tangent line to that curve. I'll have to study a little more on Desmos. But anyway, you see the point? I could graph, if I went to 1/3. This is telling me that the derivative evaluated at -1/3 is 1. And so if I graph this line on here, make it green, how about, if I go to -1/3, which is right about there, the slope of the tangent line is -1, right? So we found that place. So where did that happen? That happened at the point -1/3. Who cares? That's the answer we wanted, was the -1/3.
So on the test, if it says find the slope of 6, we just do the first part, and then if it asks for where does it have this?
Well, if it wants to know, think what the question asked. The question asked, find all the places, if any, where, find all the values of C guaranteed by the mean value theorem. So between -1 and +1, we want to find all the values of x where the function has a tangent line that's parallel to the secant line. And so in this case, that only happened at one place, one x value, which was x equals -1/3. So I guess technically we would say c equals -1/3. That's the place, right, where, take a picture of this. Yes, sir?
Why is the first blue line referred to as a secant line and the green referred to as a tangent?
Why is it what?
Why is it referred to as a secant line?
Okay, the definition of a secant line is it represents an average rate of change. So it's going to be a line that intersects a function in at least two places. It might incidentally intersect in other places, but we want to know between those two specific x values what is the line that goes through the function at x equals a and x equals b, right? And then the slope of that line represents an average rate of change. That's mainly why we used it, because it represents an average rate of change. Okay, tangent line, you know what that is. We talked about that, I think. Tangent line intersects the function in one place locally. And as you zoom in, you can see that the slope of the curve equals the slope of the tangent line. If we zoomed in infinitely, the curve would just become the tangent line.
Or is it like a cosecant line and stuff?
No. I don't know why it's called a secant. I don't think there's any connection that I know of to the secant function.
Okay,
Yeah.
that's what I was.
Yeah, oh yeah. I don't think so. All right, so let me take a picture of this. That might be useful. Oops. Okay. All right, let's do one more of these. So, how about okay, does the mean value theorem apply? No, it doesn't. You're right. How come?
Because x could be 0, because it's
Yeah.
undefined in between.
Because the function's undefined at 0, so it wouldn't apply there. End of story, right? So that one's, you're done. What if I change this to a positive 1/2?
Yes.
Now it does. Okay. All right, so, same thing. We would have to go find the derivative. So how would we do this derivative? I mean, you could do quotient rule, it's fine. But what else could you do with this one that might make it a little easier?
Change it to x and
Yeah, good. We could divide this term by term. We could rewrite this as 1 plus x to the minus 1. That makes it a little easier to differentiate. So now what's f prime? Negative x to the negative 2, right? So negative 1 over x squared. Okay, so what is the slope of the secant line? So that's f of 2 minus f of 1/2 over 2 minus 1/2, right? Because this is A and that's B. F of B minus F of A, rise and to run, over B minus A. So what is F of 2? Probably just use that guy right there. 3/2 minus F of 1/2. So we get 3/2 divided by 1/2 is 3. Over 2 minus 1/2.
3/2.
Okay, so that's just going to give us negative 3/2 over 3/2 is negative 1 again, right? So we just want to know then, when does the derivative equal negative 1? So when is negative 1 over x squared equal to negative 1? How do I solve that one?
Multiply x squared.
Well, I could cross multiply. I could also just say this. There's a little different way to think about this. For negative 1 over hand to equal negative 1, what does the denominator need to be?
1.
1, yeah. So this is true when x squared equals 1. So what's x?
1.
Well, no,
Plus or minus.
plus or minus 1. Okay, so which of those are on our interval?
Positive.
Positive 1 only, right? So x equals 1 is the only solution we can keep. That's the one that's guaranteed by the mean value theorem. Okay. Make sense? Okay, last one.
Oh,
That's okay, we're not gonna do this one. That's one. So does this make sense? When an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit. 5 hours later, the core temperature is 390 degrees Fahrenheit. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour. Okay, does that make sense? So what if we were to graph this thing? Okay, if we were to graph this, we would be putting, what would my axes be? Time and temperature, okay? And so we're starting off at t equals 0, presumably, is when we're going to start this thing, right? We're going to be up here at a value of 1500. Down here sometime late, 5 hours later, right? So down here 5 hours later, we're at a value of 390. Okay, what's the slope of the secant line connecting those? 15, real quick, what's 15, somebody with your calculator, what's 1500 minus 390 over 5?
222.
Equals what?
222.
What do you know? 222. Okay. So does it make sense that this curve right here, there's no way that the temperature is ever just going to spontaneously change by some macroscopic amount, right? It's going to be a smooth function. In fact, it's going to look like this. Okay. So there's got to be at least one place where that happens, right? That's pretty cool. So we can apply the mean value theorem. All right.